Here we go. So, as I'm sure you are all aware, the 2017 eclipse was a spectacular opportunity for both science, education, and outreach. And so the Citizen CATE Experiment was designed to try to attack all of these at the same time. We were lucky because we were able to get support from private, corporate, and federal sources to provide the equipment to all of our citizen volunteers. And as of today, our groups still have the equipment and they're still using it for various projects. On the title page here, you can see our major corporate sponsors: Colormaker, MathWorks, Celestron, and Paystar. And then we received federal funding from NASA and the National Science Foundation as well. The team is very large. We had 260 volunteers, but that's not even including the people in the room, for instance, who helped at various stages during the 3 years as we built up to the eclipse. So I'd like to thank the team, certainly, and many people in the room there for their help in making this project possible. On the next slide, we get to the science justification, the main science driver for the CATE experiment. If we go to the next slide, it was to look at the solar wind. During 93 minutes, the period of time that we had available from the Pacific Ocean to the Atlantic Ocean, we would be able to see dynamics in the corona at levels that we couldn't see from just one location, just during 2 or 3 minutes of totality. Now, the inner corona is notoriously difficult to study. The image overlay there shows 2 NASA photos of the sun, one of the corona on the disk from AIA, and the other outer region shows the white light corona from LASCO C2. But the inner part is notoriously hard to study from space. We can study it from the ground, but we have the added sky background to contend with, so the signal to noise is reduced. Of course, all of you know that during an eclipse, this part of the corona is very visible, and the Citizen CATE experiment was designed to study this particular region where there's a data gap from a lot of our observations. There's also a physics that happens here. One of the things that attracted our attention was to measure outflows in the polar regions of the sun, in polar plumes. These are thin magnetic filaments that extend mostly radially from the surface of the sun out to great distances. So the graph in the lower right shows the state of the art in the measurement of solar wind velocity in these polar plumes from 2015. The dots show measurements from various authors, and you can see that in some cases there's a discrepancy by a factor of 10 in the outflow speed. The yellow box describes the parameter space where the Citizen CATE experiment was designed to study. We could study from near the solar limb out to about 2 solar radii, and we had velocity sensitivity from not exactly 0, but pretty low velocities out to at least 150 kilometers per second or even faster speeds we could detect. So our hope is that with science analysis of the peak data, to actually redefine this problem and make some good measurements of velocity, but not only that, but also the change in velocity, to understand the energy deposition into the solar wind. So the next slide, I'm going to give you the status update. Things have been liquid here with the National Solar Observatory in Tucson. The group underwent some changes, and so as of March, I had resigned from the National Solar Observatory. So unfortunately, during the past 4 months, we have not made much progress on the data analysis. But right now, we have 3 groups looking at making movies, and I'll show you some stills and some frames from those movies where we can clearly see changes in the structure of the corona. So the threads and the magnetic fields are evolving during our time sequence. But right now, we don't have enough sensitivity and enough alignment accuracy to make a good difference in the view. In order to see solar wind outflows, you really have to subtract out the background, as they do with LASCO and other space missions. So we're working on that. That's our current focus, and we hope to make some progress in the next few months, because right now we have a draft of a paper. Our goal is to complete it by the end of this calendar year, and that will coincide with the time that we release the data. Right now, we're not releasing any digital time sequences. We have people showing digital images, of course, but we want to keep our data close at hand until we get that paper accepted, because we have eighth grade students involved as co-authors, and we don't want to see them trumped if somebody else takes the data and does science first. Right now, we have no plans for 2019, and I have no plans yet there. Of course, it's getting very late. There are some ideas, but again, 2019, as you know, is a very different eclipse, and besides taking some pictures and doing some other types of science, it really doesn't lend itself to a long time sequence. During 2017, we had 2 sites where we measured polarization, and one site was successful. I'll show you an image or 2 from that. But we think that this is a good direction to go for 2024. We think that the cost will be low enough to make this type of measurement affordable for amateur astronomers or for schools. And having that type of science data set, that we get about 90 minutes of time showing the evolution of the polarization signal in the solar corona, I think that will be very interesting science. So we're working on that. And then finally, we're continuing to work on our education and public outreach. In particular, some of our volunteers are docents in national parks in the United States. In particular, one at Glacier National Park is very active. He's using his equipment to show visitors to the park the sun every day. Of course, now it's pretty boring with sunspots, but maybe that will change without sunspots right now. We have some students who are part of the CATE project who have won awards in local science fairs. In particular, here in Arizona, I've been mentoring 2 groups of students, high school students, and other groups are working as well. And we have monthly telecons where we're updating our progress on data analysis and keeping everybody in the group together with ideas about moving forward. And I'll get to that at the end of the talk. But this is the summary, so if the beer is cold now, maybe you have an opportunity to leave the room if you really want. In the next slide, again, there were 260 volunteers, but the main group that drove the project were the CATE state coordinators. We identified people in the major states where the path of locality crossed to act as local experts. Sitting in Tucson, I really don't know much about observing in Oregon or in Nebraska. So we wanted people who were local to really decide what the best observing locations were, and also to identify the best volunteers for those sites. So we had a team of about 9 state coordinators ranging in occupation from amateur astronomers with real daytime jobs to college faculty to high school educators as well. And they really took charge. And without these people, this project would not have been possible at all. In particular, Bob Baer at Southern Illinois University Carbondale was instrumental in developing a lot of public outreach and also working with the CATE telescope as well. In the next slide, the CATE coordinator, the state coordinators also were in charge of distributing the equipment and running training workshops. So in March and April, before the eclipse, we had a sequence of 11 workshops where we distributed the equipment to the CATE volunteers and trained them during a 1 or 2 day session. These happened, in Tucson, Arizona, where the temperature was 100 degrees, and in Wyoming, where there's still snow on the ground. So it also gave us the opportunity to see how the equipment performed in a variety of conditions. After the training sessions with the state coordinators, the volunteers took their equipment back to their homes, and in the next slide, we ran through several practice runs from June through August, where from their homes, the volunteers would take data, they would upload it to a group drive, and then we would analyze it and provide feedback. So we looked at things like how well they were focusing the telescope. The telescope had an equatorial mount, so we looked at image drift to determine how well they had aligned with the polar axis. They had to insert the camera into the telescope at a certain angle. We looked at how well they did that, and also basically just things like centering the image. You can see that during the 6 weeks of practice, as a whole, the group improved, particularly with the polar alignment. And then I pulled out the best 50 sites from the eclipse day and showed the parameters there that were obtained. We certainly were able to perform well and meet our goals, particularly with the polar axis alignment during the day, which is not an easy thing to do. we're able to train our volunteers to do that at the level that actually 3 times better than we were hoping to do. Here in the background you can see, it's not quite a sample image, but it's one of the best images that our volunteers were able to take. And this is just an 8mm telescope with a 5-megapixel camera, so they're taking some high quality data, and that continued right through the eclipse. In the next slide, you can see that during the eclipse itself, we provided them with a step-by-step procedure that required about an hour and a half of work before totality. And this was matched with a GUI written by our volunteers from MathWorks in MATLAB. So on the upper right, you can see a screenshot of the focus tool that we provided them with. It gave them an image as well as an intensity slice through the limit of the sun, and then a number that they tried to maximize based on the intensity gradient. During totality, though, we wanted to make sure that the volunteers enjoyed the view. We didn't want them working hard or sweating and missing the event of the eclipse itself. So we had an automated sequence that would take sets of 8 exposures, logarithmically spaced, during totality, and they would just hit the push button, push the start button, and go off and observe it. So in the next slide, I'm showing you a movie sequence. You can play the movie. It's just a screen grab. So it's from the Weiser, Idaho site where I was at. You can see that we had some setup. It's a time lapse, but as you all know, this is really how the eclipse feels. But as we're setting up before totality, and we hit the start button, we can all just watch the event ourselves, and then we had to repoint the telescope away from the sun after totality was over. If you play that one more time, my family and I are on the left half, but the high school students from Weiser, Idaho are on the right half of the screen. You can see that they had a TV crew filming them. And if you look closely, you can see a very bright light on the camera. And during totality, you'll see that the reporter moves the camera, and she points it right down the telescope that the Weiser High School kids were pointing at totality. So unfortunately, their data is rather corrupt from the news coverage. But we're able to supplement that with the 2 calibration telescopes that I brought to the high school. So we had that experience in mind, and it actually kind of worked out for most of our sites. In the next slide, you can see sort of a variety of the locations. We had sites at the high school, like at Weiser, where we had about 2,000 people camping out on the football fields. But then there are other sites, for instance, in Dixie Butte, Oregon, on the top of a butte in the middle of nowhere. Some remote locations in Nebraska and in South Carolina as well. But then the real concentrations of people were found at some of the universities. So in Carbondale, in Cooksville, Tennessee, and in Orangeburg, South Carolina, we had stadiums where the CATE observations were taken on the 50-yard line, and there were 8,000 or 10,000 cheering fans in the football stadium. That must have been a spectacular place to be. On the next slide, we see another group. This is a group from Idaho Falls, and there's a sample frame. The shortest exposure that we took was 0.4 milliseconds. That showed the prominences very well. The group led by Julia Kamenetsky from outside of Salt Lake City went to Idaho Falls on a geology field trip. Apparently the students liked the eclipse a lot more than they liked the geology, so I'm not sure it worked out the way that she had planned the trip would work out. But they took some excellent data, and it was wonderful to have them involved as one of the teams that traveled. In the next slide, though, my favorite team story from a team that traveled was a local high school group here in Tucson. We went to Pawnee City, Nebraska. They were followed, or maybe I could say hounded, by the Discovery Channel film crew during all of their training here in Tucson, and then also in Pawnee City, Nebraska. And you can see the film crew was filming them as it rained while they were trying to set up. There was a downpour. So the students were huddled under the tarp trying to protect the telescope from the rain, and the laptop was out there getting wet. I don't want to even think about the USB wires going back on the ground there. But somehow, in the next slide, you can see that conditions cleared, and they managed to collect data, and they're jumping for joy. This is a little preview. So the image on the left is a radial gradient filter image from their site, and then we do a SOAP filtering to enhance the edges. Again, data from their site on the left, on the right. So that's a sample of some individual sites, but in order to combine the data, we've got to use timing information. So on the next slide, you can see that we included a GPS daughter board in our Arduino camera box. The Arduino was strobing the camera with a hardware strobe to sequence the exposures, but we also looked for GPS location and timing information from every site. We think that we have about 30-meter accuracy based on our sites in Weiser, Idaho, for the location of every observing site. And our best estimate is that it's about plus or minus 100 milliseconds accuracy with the timing. We collected about 24,000 GPS timing strings from all of the sites. We calibrated the local laptop computer with the GPS time. And then for every image, we have a time string stored using the local laptop time. We, again, cycle through a sequence of 8 exposures, so our sort of inherent time resolution is 2.1 seconds between HDR images. So having 100 milliseconds accuracy is very good. So when we start to combine that data, in the next slide you can see plots of our coverage. How do we do during eclipse day? And as you know, things went really well, better than anyone expected on the day of the eclipse in terms of weather. We had about 83 out of the 93 minutes where we collected data, so about 90% coverage of the event. On the top, maybe it's a little difficult to see, but there's a plot of universal time on the x-axis and the number of sites that we have on the y-axis. You can see some of the gaps, but sometimes we have 2 sites observing the corona, other times we have up to 5 telescopes looking at the corona during totality at the same time. The graph on the bottom shows the gaps a little bit better. Time again is on the x-axis, and then site longitude is on the y-axis. The little line segments show coronal observations during totality from every site. And then the pink vertical bars show the time gaps that we have. We had one site where the instrument failed, and then we had clouds in the middle in the Missouri, Kansas area, and then a few other problems scattered throughout the western or the eastern part. But having 90% coverage is something that none of us ever dreamed of. I was going to be happy with 50% coverage. So this is a real tribute to the practice sessions and the dedication of the volunteers that we had, that they collected so much wonderful data. So I'll step you through a few of the images now. And the next slide is a 40 millisecond exposure taken from one of our sites in Salem, site number 2. The details of the optics are shown there. The telescope was donated by Daystar Filters very generously. We bought the cameras from Point Grey, now owned by FLIR. And again, 40 millisecond exposure saturates the prominences, but it shows you the inner corona and some of the structure there. In the next slide, you can see 40 milliseconds that shows you the middle of the field of view with the pixels in the inner corner saturating. The good thing about the camera is when pixels saturate, they don't bloom very much, and so we're able to just ignore them and cut them out when we're producing the high dynamic range image. Finally, the last image shows you a 400 millisecond exposure. Again, we're getting details out of the edge of our field of view. In the next slide. But most of the corona, the inner corona is sort of saturated, although we start to see structures out at the edge. What we want to do, of course, is to remove this steep radial gradient from our data, and so we need to measure it very well. In the center, we have a graph showing intensity measurements from 2 sites, one in Oregon, the other in Idaho Falls, so separated by about 300 miles under very different atmospheres. We have the log of the coronal brightness on the y-axis and the log of the solar radius on the x-axis. So across a factor of 300 in intensity, These two telescopes are measuring the coronal intensity almost identically. You see the lines almost overlap. So we have some very good response from our equipment, even if it's in different locations. When we remove the radial gradient in the next slide, you can see a filtered image. This one is from our site in Carbondale, site 41. This is produced from a set of 8. Now, of course, we sequence through sets of 8 during totality, so every site has about 60 of these sets. And we're working on now aligning these. If you can blink back and forth between this image and the next one, you'll see another image from Tennessee. And now if you go back, you'll see that there's a rotation and a translation between the two. And this is now where we've been spending most of our efforts, trying to align these coronal structures. And as many of you know, this is a difficult problem. The main reason is shown in the following slide. The moon is obviously the most contrasty object in the frame, but because our observing locations are north or south of the center line, and because the moon actually changes size during the path, or across the path of totality, we can't use the moon to center these images. So we have to ignore the moon and use the lower contrast coronal structures to understand the rotational and the translational offsets. There's data from Jumier in there that shows how the lunar radius is predicted to change across the path of totality, and the stars are measurements from the CATE data, what we measured for lunar radius to be. You see we have about a 2 pixel, plus or minus 2 pixel scatter, but the agreement is really nice. What we've done to try to get around this is to enhance further the coronal structures. In the next slide, you see a Sobel filter combined with some spatial averaging. We're trying to pick out threads, individual threads in the corona, and use those to align the rotation and translational offsets between the sites. And we've made a rough cut movie of this. I'll show you a frame in the following slide, in the next slide, where we can see some outflows. Again, maybe I can share my screen if you want to see a time sequence. But we do see what looks like the remnants of a CME, or the late phase of a CME flowing out of the southeast part of the sun in the streamer, with outflows of about 10 kilometers per second. But then in both poles, both the north and the south poles, we do see more rapid events, changes in the coronal threads. So I'm not sure how well this will work. I hate to pester the person running the slides, but the next 5 slides show a sequence, a time sequence of the south pole event. And if you could sequence through those and then back, you'll be able to see that a set of threads changes, certainly changes between 2 and 3 threads. And then we also think that there are some outflow velocities in these threads. But you can also see that we're nearing the signal to noise of our first cut movie, because the noise is pretty large at the edge of the frame. We really need to code out all the data and to beat down that noise and get a better signal to noise ratio to track features. But that's the type of event that we see in the poles. And then the 4 slides that follow that are a sample of a thread evolving in the southeast, and if you move back and forth between those, you can see what we think are outflow motions and untwisting in this coronal thread as the magnetic field of the corona rearranges itself in the late phase of the CME. So there's interesting evolution that we see in the data. It's not quite the solar wind speed measurements that we're hoping to get to, but I think that in the next few months we'll be able to get the data aligned well enough to start looking at difference images and hopefully see some outflows along these stationary threads. In the next slide, I just want to show one slide of the polarimetry data. We had 2 efforts in this direction, but one succeeded. And from Teutonia, Idaho, David Elmore was able to collect images. This is with a CATE telescope with a Cox polarimeter. Not very expensive. So he was able to measure polarized brightness in the upper left. And maybe the most interesting thing you can see there is that the prominence itself, that the limb is dark, is a very unpolarized signal in the continuum. And then the angle polarization, this is well known from Thomson scattering in the corona. It should be perpendicular to the radial vector, and that's what David sees in his data. The color table is an elaborate way to show the direction, but the arrows show you the direction of the polarization at those locations. So that's the first look at the science that we had. The next slide tries to summarize the outreach. We had events leading up to the eclipse where we think we reached something like 17,000 people. On the day of the eclipse, we had events at high schools and at college stadiums, we think, and in small towns across the path. For instance, in Weiser, Idaho, they weren't planning on running any special eclipse events, but they did because of the CATE project, and they ended up with 20,000 people in their small town of 10,000 folks. So we estimate that a lot of people showed up to the CATE locations and participated and got some education, some more knowledge about the eclipse and the science behind it. We had a lot of coverage in print, radio, and TV, and then Congress got interested, and I was honored to testify back in September about the CATE project to tell some of the stories that the teams experienced on that day. And then finally, where do we go from here? On the last slide, I can show you that we have a web page. It's blocked, I guess, but it's citizencate.org. We also have a Facebook page. If you're interested in being involved, and I would encourage you. I'm talking, of course, to an audience of eclipse experts. And if any of you are interested in becoming involved with these students in solar experiments or astronomy experiments, they are very eager and very excited to continue working with their equipment. Some of them have taken lunar occultation data. In the top left is the sequence of the reappearance of Aldebaran behind the dark side of the moon using the CATE experiment. Again, we had several women students from Arizona running science fair projects, doing instrumentation and data analysis with our data. And then, of course, the telescopes are available to travel to other eclipses. And if sunspots ever return to the sun, we can take some amazing sunspot images as well. So please, if you're interested, send me an email offline or let me know, and we can get you connected with the group, and or you can just pick one high school or one location that you might be interested in helping. That would make a huge difference. Thank you for your time, and I'd be happy to answer any questions.
Thank you very much, Matt, for your presentation at the location in Arizona. We have time for a few questions. Lance can't see you, only hear you, so please say your name and your question. Do we have any questions?
Matt, that was fantastic. I'm Judy Anderson. Jay and I observed from Tetons, and we also had polarizing filters, and we also saw that lower plume completely disappear when we went to a second filter and come back when we went out during cross-polarizing filters. But the project is fantastic, and I would commend you in trying to recruit the students that have those telescopes to be your ambassadors for future eclipses. Phone beside me is ringing. And also to find ways to take those people who, especially the winners of the science fairs, to other events around the world. If you have no plans for Chile or Argentina, there should be ways to raise money to take a couple of students from your project and show people how much they can do the way they did that. That is fantastic. So absolutely great work.
One of the ideas I have is to take the winners to the Chilean eclipse. Unfortunately, the teachers at the school have other priorities, and because it's not in their backyard, this may not happen. But certainly I think the groups that are involved are really motivated, and we did a lot with 2017, and we're hoping to continue their experiences.
Okay, thank you. Are there other questions?